Alright, so air enters through the intake, past the inlet guide vanes. The inlet guide vanes are going to work to keep the airflow, remove the turbulence of the airflow, going on to the compressor section. On the compressor of the 250, we've got an axial compressor section here, and it's going to go to a centrifugal compressor as well, and they all spin on the same shaft, as you can see. So these are the rotors. On this we've got 5 or 6 stages of compression. A stator and a rotor constitutes a stage of compression. So this is a rotor, and it goes stator, rotor, stator, rotor. And if you have a look here, this is the compressor case half, or one of them. So that there will just fit on like that, and you can see that the stators, which are on this section, are in between the rotors. So how it works in terms of compressing the air is this. So the first fan is going to work like, just think of your conventional ceiling fan, right? It's going to push the air back, pull and suck the air through the inlet guide vanes, and then what's going to happen is the air is going to hit the first stator section. So since the first fan's pulling the air in, we've got a lot of velocity, right? What the stators do is they impart velocity for pressure, and considering they're also angled, they're going to direct the airflow at the right angle to hit the next rotor section. When it hits the next rotor section, that process is going to be started all over again. The rotor is going to speed up the airflow onto the next stator section, which will transform or impart velocity of air pressure to pressure, and that's going to continue all the way up. As you can see, the blades get smaller as you go along, so not only is the airflow increasing in velocity and pressure, it's also decreasing in the amount of area that the air has to be in, which will just compress it. Then as we go on, you'll see what's called the diffuser scroll. Looks like a scroll from the bakery. It's this big unit here. What that does is now, after the compression, we've got a whole lot of really fast, highly compressed air, right? But oftentimes it can be quite turbulent, and that's not what we want for the later stage of combustion. So what the diffuser scroll does is there's a series of diverging ducts which slow down the airflow, remove the turbulence, and prepare it for the most efficient combustion. So as it comes out of the discharge of the diffuser scroll, it's going to go through these sort of angles. Inside of there is what we call angled vanes, leading on to the compressor discharge air tubes. So this is a reverse flow engine. So what those angle vanes do is, because the air now has to go around this split turn, they're going to direct the airflow right through and essentially reduce the loss in speed and pressure as it goes around this corner. Makes it a lot easier for it to do so. Now we're going to get down to the combustion section. This here is the outer combustion liner. So air is 50-50 split from the compressor section down the transfer tubes. It's going to come down into the combustion section. Here we have your fuel nozzle located directly in the center, as you can see. That's going to allow the fuel to go directly onto the combustion can, and the igniter here. Now, as the air combusts in the combustion chamber, it moves on to the various turbine sections, which makes the power for your N2, so your rotor system. The first rotor, or the first turbine that you have, is what you call your gas generator turbine, and so that is directly coupled to the rotation of the compressor. The main priority in the engine, in order for it to be self-sustaining, is to spin up the compressor. If you don't use the priority energy produced by the flame to spin up the compressor, then you will not be able to continue and be self-sustaining, which is what you overall want to do. So after the gas generator turbine, you'll move on to the various different stages of power turbines, as you call it, and that's what's going to be driving your rotor system, or whatever you want to drive depending on the application. There's the output shaft here, and you'll see that if I just turn the power turbine, you'll see that the shaft turns. So that there is the last rotor stage of the power turbine, which is in the exhaust duct, as you can see here, which is just those turbines there. So if I turn them, they're just like a rotor, just like the axial compressor at the start that I showed you. The N2, which is your power section, and your N1 is your compressor section. So they're not mechanically coupled to each other. So for reasons being that if your rotor was to overspeed or underspeed, the differential between your N2 and N1 is how your fuel control unit decides how much fuel it wants to inject in the engine, and as a result, how much it wants the compressor to spin up. So if the pilot decides, oh shit, I need to climb out of this gully right now, we need to put on a whole lot of power, he's going to pull up on power. That's going to increase more fuel into the combustion liner, which is going to drive the gas generator turbine, which is going to spin up the compressor faster, compressing more air, which will allow more power onto the power turbine, driving the rotors faster. As well as that, you can see here on the axial compressor section is a bleed band. So this is where air is utilised for a bleed valve, which I'll explain a bit later when it's on. But essentially a bleed valve is because the starter can't generate enough force to be able to push a whole lot of air through the system for starting, it needs to be able to bleed that air off upon the start just to make it easier. So when this is all sealed out, you can imagine with the rotors and the stators, there's a whole lot of energy required to be able to pull enough air through the system. And the starter, which is usually mounted down on this pad here, just simply doesn't have enough power if this was fully sealed up. So what happens is when the engine is not started, the bleed valve here is open, allowing compressed air to be dumped out of this port here, meaning that the compressor, the axial compressor and centrifugal compressor, is allowed to spin up faster. Good thing to have a look at here as well is the anti-icing system. So because you're pushing a whole lot of air through your compressor super fast, depending on your operating conditions, the pilot might decide or might need to apply anti-ice. So what happens here is air is bled off of the compressor scroll, where the air here is still around about 200 degrees, just simply because of the compression. Because it's about 200 degrees, that warm air is allowed to be bled off through this unit here. This is an anti-ice valve. Usually there's a lever on here that's actuated from the pilot, so he pulls that out there, which allows hot air, 200 degree air, compressed air at this point, through a series of tubes, I'll show you them later, into these ports on the side. So what happens there is the air goes into this inlet guide vane ring. So the air is distributed all the way throughout and then into each one of the vanes. So the air goes through each one of the vanes on the inside. And then as you can see, I'll try and zoom in, on the back of the vanes are these little slits, inlet guide vanes. You see those slits along them? So that 200 degree air, which has been taken from the compression stage further along, is rerouted back to the inlet, and then that warm air goes right throughout the whole system, stopping it from icing up. Pretty critical factor here is the clearance between the compressor case half and each rotor. So you can see that there's very close tolerance there. So any air escaping around the top of the blade there is not getting compressed efficiently. So what the designers want, what an engine designer wants, is the air to go through the airfoil of each vane. So you can see that it's all very close tolerance stuff. So there's a stator, which I'm showing you on the other half. So you can see that it's very close tolerance there. So yeah, it's all one solid unit. Just pulled up an image here. There's a really good look at the centrifugal compressor that is directly after the axial compressor that I've just shown you. This section here, this ring, those wee vanes there, or the start of the centrifugal compressor, is what we can see on our engine. Just show you that now. Have a look around here. There they are, right there. So that's what it looks like housed in the unit there. How it works is essentially these are sort of like a, well, it's in the name, centrifugal, right? So the air is forced into these inlet vanes and then it's pushed out, and the shape of where the fins distribute around the whole unit forces air out very fast, and you get this big swirling motion. So that's going to compress the air into the diffuser scroll. And like I said, that air is very turbulent. It's not very desirable for combustion. So the diffuser scroll slows it down, imparts velocity for pressure, and essentially just prepares it down these tubes for combustion a whole lot better. Okay, so now we know more about that, we can talk about how things are lubricated. So there are various different bearings along the whole engine, axially. So you think there's a big shaft flowing right through here. There's a shaft that's connected, like I said, to the compressor. From the compressor to the gas generator turbine, and from the turbine assembly to the output shaft through the accessory gearbox here. So because of that, there's a whole lot of bearings that we need to lubricate, because the temperature in here is in excess of 600 or so degrees. It's important to remember that a limiting factor of all engines is the temperature at which it can run. Sweet, so now I've got the bleed control valve back on, so I'll just show you how that works. Like I was talking about before, we've got bleed air from the scroll, 200 degree air, that's at its hottest point for compression, exits the scroll back around this tube into a sonic venturi. So what it is essentially is a calibrated orifice inside of this unit here that senses the speed of the air exiting the scroll, and when the speed of the air gets up to its proper operating limit, this valve will be pushed closed. As you can see, that's going to push close, just going to close off the bleed band, meaning that 100% of the air that gets sucked in the intake is forced through into the centrifugal compressor and then onto combustion. Now, just to explain a bit more why, you think a good way to think about it is you just imagine blowing through a straw. It's quite hard, right? It's quite difficult because it's not so much of an opening. You need a lot of pressure to do that, right? But then you think you're blowing through that same straw and you cut a hole about midway along the straw. There's the hole. It becomes a whole lot easier to blow that air through because you've got air vents, which allows the air to move faster. And in this case, doing that will allow our axial compressor and centrifugal compressor to spin up faster, only on the start. Once the starter has moved things up fast enough and we're starting to get some combustion, doesn't need it, closes off. Simple as that. Anti-ice tubes are now installed as well. So like I told you about this valve before, these two tubes run from the same union. They pop out, they are routed all the way along and into the side of the inlet guide vanes. And then once they enter the guide vanes, right around the front support assembly, it's all aerated. And on the back of each guide vane, like I showed you, there's those wee slits where the hot air is pushed through the engine. If you look in the centre of this engine, this 250 is quite well painted, this wee bit here. This is the accessory gearbox. So the drive coming from the power turbine, all of the power that we want from the engine is transmitted through the accessory gearbox. It's called the accessory gearbox because we use it via a whole lot of different gears to drive a whole lot of different accessories. So on the back here it gets a little bit busy. A lot of these simply run on black magic, a little bit complicated, but you can sort of identify what they all do. On this pad here we mount the starter generator. So the starter generator is a DC motor that spins over the driveline for start, but then once the engine's running at its 100% RPM or idle RPM, the engine decouples from the DC starter function and starts turning into a DC generator. That is then transformed to AC throughout the aircraft at different points depending on the application. To the left there, fuel pump, fuel filter, that's driven from the engine. Main drive line there, that's going to go to your rotors like I showed you before. This beast up here, all the different ports, is a hydro-mechanical fuel control unit. So the input from the pilot is this lever here. This is controlled, this is a bell crank here that when the pilot pulls on, wants more power, does that. This device here is taking different sensing parameters from different points along the engine to decide how much fuel is injected here, which then decides how much power you get out of it. So there's a whole bunch of complicated parameters around that. It's also taken from your N2 governor, which is sensing your rotor speed and a lot of other parameters as well. Another wee bit to show you, this is the pad for a hydraulic pump which is mounted on there. It is just not being used for this application, but if you were to put a hydraulic pump there, that's gonna run sometimes your hydraulic servos for your flight controls or other things. Around the side here, these are your N2 tachometers. That's your N2 tachometer, and then there's your N1 tachometer. So sensing different portions of the engine. So like I said, there's your N1 and your N2 is your power section. This engine might also be fitted to an aircraft that requires bleed air for other applications. For example, you might be in an aircraft that's going quite high and you need to pressurize the cabin. So these two, they call customer bleed ports, exist for that reason. So these two, there's one there and one up there. So the customer or the aircraft manufacturer can take bleed air from there if they want to.